the goal is this monocular. Monocular means only one image and then we want to find depth. So it's a very challenging task because generally we require two images for geometrically finding the point, but here only we have one image. Now, so which means that the parallax based cues are not there. So we have seen the Eiffel Tower example, right? There was shift because the two images were taken. Now, because only one image is taken, that shift cue or parallax cue is not there, but there are some other cues. For example, if you look at this image, the second image, the bottom image, so yeah, so if we look at this second image, so we are seeing various cars, right? But some of the cars seems very small. So actually this size, like size of objects tell us the depth, how far. Like for example, we know that all these cars should have the same size, approximately the same size. So if it appears very small compared to the car which is larger here, so that gives us a depth cue. So that small car must be further away from this big car. So this kind of, the size is a very big cue. So there is object sizes. If I have some idea about object size and it seems very small compared to what size it should have, that means it is very far away. So this way there are cues. So another cue is occlusion. For example, we can see that this car, this kind of let's say black car is occluding this white car. So we know that the black car must be in front of the white car. So this also is a depth cue. This occlusion also gives us depth cue. Then something called vanishing points. For example, these rail lines, it appears to converge, right? But we know that it should not converge, right? I mean, they are parallel lines. So, but this thing that it appears to converge, that also gives us a depth cue. So anything which is further down there is far away and than anything which is closer here. So these kind of, there are various cues which are all cues from a single image. It doesn't require two images. So we can use these cues also to find the depth, and that is the idea. But it is not possible to do it in a geometric manner like the way we had done it for stereo, like all these operations like find out the point correspondence and then draw two lines, and wherever they intersect, that is called triangulation. Wherever they intersect, that gives the 3D. That's the geometric way of doing it. So we cannot do that geometric way, but we can still, using all these cues like size of the objects, then vanishing points and occlusion, all these cues we can use and then give a then we can also get a depth, and that depth is up to a scale, correct up to a scale, because geometrically we cannot do it. So generally it is correct up to a scale, and it's done completely based on data. So what it means is, if you give me a lot of data like image and corresponding depth, and this depth like you can capture using various kind of sensor like LiDAR. There are LiDAR sensors which gives us depth. There are also Kinect kind of sensors which gives us depth. So basically some depth sensor, let's say. So you have, so you collect the image and a depth sensor which senses the depth, and you have this corresponding image and the corresponding depth. So if you have this and you need lots of pairs like that, then we can get this supervising. Actually, there are two ways of getting this depth from a single image. One is the supervised technique. For supervised technique, definitely you need these pairs of data, which means you need the image and the corresponding depth. And then you will have some network which will map this image to its corresponding depth. So that's all supervised techniques are there, and we'll look at two different algorithms or two different networks. One is called multi-scale deep network, another is called U-Net. So this will look at, and there is also unsupervised. Unsupervised means that you don't have the ground truth depth map. So you have the image, but you don't have the ground truth. So here the technique that we'll look at is called left-right consistency, which means that instead of having the depth, we'll have two images, the left and right image in some sense, and using them, using the right image as a supervision, it's called self-supervision, and we can obtain the depth. We can train the network for the depth. We'll see that will be the, but it doesn't require ground truth depth. The first method, the supervised technique, requires that we get the ground truth depth. The unsupervised doesn't require ground truth, but we'll get the disparity by taking another image. But of course, that's not the same as supervised. So that's why calling as unsupervised, or actually it is self-supervised. So we will see now each of this architecture. For example, we will look at multi-scale deep networks. So as we have said, this is a supervised technique. So you need this input image and the corresponding depth. Now in this network, it can be divided into two parts. One is this coarse network. Coarse means it does a rough estimation. So it also gets, like you can see, this various layers, coarse one, which produces various features. So you can see this coarse 7, it looks like a depth map. So actually it is a coarse depth map. So this network gives you a coarse network, coarse depth, and then we have a fine network also, which, so basically this whatever the coarse depth we have obtained, that is fed into this fine network. So the fine network also gets the input as well as this coarse depth map, and that it takes and then again do a series of convolution to refine it. So that is the idea. So this network, it is called multi-scale because it is operating in two scale. One is the coarse scale, another is the fine scale. In coarse scale, you take this input image and pass through a series of convolutions, and the operations are given here. For example, your first convolution layer, you convolve it with 11 cross 11 filters with stride of 4 and with 2 cross 2 pooling, like that. So because you are doing stride 4 and 2 cross 2 pooling, it will reduce the size by 1/8, right? Like 1/8 input image, like that. And then again the next is again 5 cross 5 convolution, 2 cross 2 pooling. Because of this 2 cross 2 pooling, it will reduce the size by half. So it goes from 37 to 18, like that. And then you have a series of convolution. Again, you do a series of convolution where you are not changing. So this course 2, 3, 4, you are not changing the size, but you pass it through many convolutions, 3 convolution layers with non-linearity and all. So and then you have this 5th layer where you again do some kind of a pooling, and because if its size further reduces, then 6th layer it again reduces. You do 1 cross 1 convolution, yeah. So like that, and at the 7th layer you get the coarse estimate for the depth. So and this is the coarse network, and then what you do is feed this coarse depth into the finer network. So in finer network also you start with this, again you start with a series of convolution. First you do 9 cross 9 convolution with stride 2 and 2 cross 2 pooling, which will reduce the size by 1/4, right? It will do this size by 1/4, and then you feed in this coarse, the output from the coarse network, and these are concatenated then, and then again pass it through some convolutions, and then you get the refined depth. So this, it is doing it in 2 scales, and therefore it is called multi-scale deep network. So coarse network is predicting the overall depth of the scene. So the goal is that you do lot of convolutions, 6, 7 layers of convolutions, so that you have a bigger context that you look at, and you produce a coarse depth map, and the fine network will then refine it to predict a more accurate depth map. So that's the whole idea about this. So the coarse network has deeper layers, so it has a larger receptive field, and on the other hand, final network has lesser, less deep, but it uses anyway the information that we get from the coarse to refine and get a finer depth map. So that is this, and these are some of the results. So these are the images which are input, and then these are the coarse estimate. So you can see the coarse estimate by itself doesn't give much, but then the fine estimate gives more structure. So you can see somewhat like the ground truth, though it is not still as good, but at least something.